Okay, let's begin with command responder. The command responder is the final stage of wake-word detection pipeline. Once the wake-word is confirmed, the responder triggers the appropriate actions such as tuning on a device, logging the detection, or sending a control signals. However, it works, it's received the detected word along with its confidence score and timestamp. Then check whether this is a new detection or a simplify a repeat. If it will be valid means it's execute a predefined response like the flashing LED sending output to another module or recording the event in a log. The responder is also a customizable. On microcontroller, it may control hardware, while in voice assistants, it can launch system commands or wake up the assistant. The default setup simply prints the detection result to the console. Okay, next we will see a listening for wake words. The key ideas here is that microcontroller is always running in a loop, continuously monitoring audio from the microphones in a real time. There are few core functions at works here. First one, setup function. This runs only once at the time. It initializes everything we need, the TensorFlow Lite model, memory, buffers, and any hardware components like the microphones or LED. Thinks of this as the system boosting and booting up and getting ready to listen. Next, loop function. After setup, the program enters the endless loop. Inside this loop, the system keeps checking the incoming audio stream, running features, extractions, and performing inference. This is what that keeps the device always ready to respond. Third, future extraction. Raw audio by itself is not useful for the model. So the system converts audio into a spectrogram, basically a frequency map of sounds over time. This makes patterns its speech easier for the neural network to recognize. Fourth, model inference. Once we have the spectrogram, it's feed into the TensorFlow Lite model. The model classifies it into a categories like yes, no, silence, or unknown. Command processing. Finally, the system checks if the model output matches a valid wake word, if the confidence is high enough, if the trigger of the appropriate response. Therefore, the example lighting up an LED, starting another process, or activating a voice assistant. Then start the deploying on microcontrollers. Now that we are built the and tested our wake-word detection model, the next step is deploying it on the microcontroller. Unlike the powerful computers or cloud servers, microcontrollers have very limited memory and processing powers. This means we need to optimize our machine learning model so it can run efficiently in this resources constrained environment. This is where TensorFlow Lites for microcontrollers comes in. The TFML allows us to take a trained model and convert it into a format that's small and fast enough to run on embedded devices. Here the process. First one, training the model. We start by the training our wake-word model on a datasets of audio recording for the example spoken words like yes or no, converting to TensorFlow Lite. Once it trained, we will export the model into a TF flight file. That version is already optimized to lightweight inference. To reduce a memory usage even further, we are applying quantization. The strings, the models sizing the high precision numbers into a smaller representation, while still keeping the accuracy good enough for a real world users. Compiling and deploying. The TF Lite model is compiled into a firmware and flashed into the microcontroller flash memory. From here it runs directly on the device with a very low latency. Nowhere which hardware we can use. Some of most popular microcontroller platforms for wake-word detection includes Arduino Nano 33 BLE Sense, a beginner-friendly board with the built-in microphones and LED. Spark Fun Edge, powered by the AMQ Apollo 3 microcontroller, designed for the always on ultra low power listening. STM32 Discovery Kit, a higher performance options greater for more complex TinyML application. Finally, after the deployment, we test the system with real audio. We check whether it detects the wake word correctly, confirms the latency is low, then make sure it operates smoothly without draining too much power. Next, optimizing performance. Once our wake word detection system is running on the microcontroller, the next step is optimizing. We want to be accurate and efficient and fast. Let's break this into three key areas. First one, reducing a false activation. Once a common challenge is when system mistakenly thinks it's heard a wake word. To reduce this false positive, we can first one, adjust the confidence threshold so that only strong predictions trigger a response. Second, applying data augmentation during training. For example, adding a background noises, changing pitch, or mixing a different environment. This makes model more robust in real world situation. Third, test across diverse accents and voice to ensure the system works well for the different speakers. Second one, power efficiency. Since the microcontroller often run on batteries, power efficiency is crucial. Some ways to save energy include sleep modes, optimized memories, low power processing system. In the sleep modes, putting the device into a low power state with it's not actively pre-processing. Second one, optimized memory usage, making sure the model is neatly into the microcontroller constraint, avoiding a wasted resources. Third, low power processing, using the hardware specific optimization to keep the listening without draining too much battery. Last one, latency reduction. Finally, we want the system to respond quickly when the hears the wake word to reduce latency. First one, minimize model computation time by using a lightweight neural network and quantized model. Second one, streamline inference so that classification runs in milliseconds. This ensures that what we all say the wake word, the device responds instantly, creating a smoother user experience. For the few false activation, low power consumption, and faster response, with this optimization, we can take in a working wake word detector and make it's reliable for the real world everyday users. Okay, I will stop here. Next video we will see about Arduino running the examples and warping up.